Continue.
This meeting is being recorded.
Thank you. Okay, and welcome everybody to our official start now of data mining. We are today going to cover up the last things about PageRank, which will be a little bit in the notes, and we have a project now posted, programming project, and your midterm exam, which will be next week. We'll talk about all of those things today in class. Before doing that, though, I want to start with two issues that were posted over the weekend. Very good questions here, and make sure that those get answered. Both of these two issues are very closely related, so I'll basically answer them in one go here. They're both related to the alpha value, or this primitivity, or the different eigenvalues of our p-bar matrix. In order to do that, though, so one thing before the issues is that I did make a mistake on our notes last class period, so I want to get those corrected. And I'm also going to give you some of the answers to some of the future notes packets really quick here, so that you can verify your work going forward. So we're going to be taking a look here at the second and the third note packet, all of the different runtimes here. The first thing is the mistake that I made. Let's come over here and let's see. In a second, in order to answer the issues, I'm going to try to have both of these windows up side by side. So hopefully this text is readable to everybody. If not, let me know and I'll make it bigger. But I'm going to try to have both of these texts side to side. The particular problem that I had last time, again, I made a calculation mistake. Calculate on problem 3 right here. This is the notes packet 2 on problem 3. I made a calculation mistake stating the runtime here of this XP multiplication. My mistake, the thing that I said that was wrong, is I said that this takes the runtime is theta of n z of p times n. This is the thing that I stated, but this is wrong. So this is incorrect. And what it should be correct is that the runtime is just theta of n z of p. That this extra n over here, this is the part that shouldn't be there. The n shouldn't be there. That's a quick sanity check of this. So I did some sanity check stuff last time, but I did not sanity check this in detail enough, this part right here. As a quick sanity check, we recall that this n value here should be, or semantically what it is in our case, the semantics of n. The meaning of n, the semantics, is that this is the number of web pages, or more generally, the number of nodes in our graph. And we have a very, very large number of web pages that on Google, it's on the order of something like 10 to the 15th is the number of web pages. And so this really needs to be linear in the value of n here. Anything super linear, anything bigger than linear is just totally out of the question. Quadratic algorithm on the number of web pages is out of the question. We need something with a linear runtime. And one of the things that the paper stated is that our NNZ of P, the number of non-zeros of our matrix, that we should assume that that is upper bounded by the total number of web pages, that it is O of n. And so this runtime down here is in fact linear. This runtime up here would be quadratic, that this n and z of p get replaced by n. That n times this n is quadratic. So again, I made this mistake here on the runtime of x times p. The mistake was that I included an extra factor of n. That factor of n should not be in there. The ultimate implication of this mistake is, let's see, part 4 down here is where we got the actual runtime. The actual final runtime should look something like log of epsilon divided by log of alpha times n z of p, like that. That's the correct final runtime. Question? Question is, am I recording? I think so, but let's double check. Yes, I am recording. Thank you. And the audio is on, and it is sharing the screen. Yes. Yes, Tyler.
Didn't we say that if you're multiplying the sum of sparsely, that's the sparse thing?
Yeah, this is a good question. The question is, if we're multiplying something sparse by something dense, what's the correct order for things? And we're in your programming assignment that you'll actually have to implement this equation right here. And you'll be using the PyTorch library to do this. And PyTorch only supports sparse times dense. Sparse on the left and dense on the right in PyTorch. This is PyTorch. In the previous notes packet, notes packets 1, we saw how you can use transposes to convert this into a sparse on the left and a dense on the right, whereas right now we have sparse on the right and dense on the left. But this is something that you will have to consider for actually the implementation, which we'll talk about in a little bit. But in order to convert, again, sparse to dense, use transposes, use the transpose. And the notes 1 talks about this, has some examples. Notes 1, Roman numeral 1. Good question. So the correct answer for this runtime, again, log epsilon over log alpha times the n and z of p. Problem 4 right here asks you to repeat all of those steps. I will just, I won't repeat those steps for you right now, but I will tell you what the answer should be. You should get the log epsilon over log alpha times n squared. And P is about using a dense matrix instead of a sparse matrix. And so we can see that the dense matrix has a significantly worse dependence on the n value over here, quadratic instead of linear. And this is why dense matrices just can't be used on pagerank for these web graphs, these very, very large graphs where n is in the like 10 to the 15th for the actual web page. So you should go through those steps, make sure that you can do them, and come up with this same answer on your own. You'll know that you got the right answer, that you did the steps correctly if you get this answer. I'm going to do tell you one more correct answer here, and then I will go back to those issues. In order to tell you the correct answer, we're going to go to this PageRank 3 notes, and I'm going to tell you the answer for this big exponentially accelerated algorithm right here, this problem 3. There's a lot of things going on in this 3. It walks you through many different steps. At the very end, what number is it? The final runtime over here, part 4 again, is going to be O of, now there will be 2 logs, log of log epsilon over log alpha times n cubed. In this method, the reason this is called exponentially accelerated, this log right here is the exponential acceleration. So called exponentially accelerated because of this log right here. Again, I've skipped all the intermediate steps here, just telling you what the correct answer is here. You should go through all those intermediate steps, make sure that you can do them, and you'll know you did them correctly if you get this answer right here. Any questions about those? Yes.
So with the cubic term there, is the log enough to offset that?
Yeah, so that's a good question. So this log is going to shrink this part over here a lot, but this log is not being applied to the n value over here. And is this exponential acceleration like a good algorithm? And the answer is that you would not be able to use this algorithm on a web graph because this n cubed here is just 10 to the 15th cubed is an astronomical number, would never finish. But if you needed a smaller, if you had a smaller graph and you needed much better accuracies or much different alpha values, then this could be a potential problem or a potential algorithm that would be good. One of the things that you'll have to think through here, so part 5 here, under what conditions is this exponentially accelerated power method better than the standard power method? And so that's an important thing to think through that and make sure that you'd have an answer for that for the midterm exam, which again, we'll talk about in a minute. Good question. Okay. What I actually wanted us to start talking about, though, after we have these answers, is these 2 issues posted over here. And these 2 issues are, again, closely related. They're asking about, like, what's the meaning of this alpha value in our runtimes, and how does that relate to our different things that the paper talks about with the p-bar-bar matrix. So for example, there's this thing called the eigengap, the difference between the top and the second largest eigenvalues. How is that related to alpha? Why is alpha appearing in this runtime when it seems like a linear algebra specific thing? Why is, like just all the different questions about this alpha is what these 2 issues are talking about, and what we will talk about next. In order to talk about those, I'm going to come back over here where we have theorem 5.1 on the paper to the left-hand side over here. And on the right-hand side over here, I'm going to jump us down to problem 7. This is in the notes packet 2, problem 7. This problem 7 is going to be particularly important for our for your homework assignments. And so we'll keep this in mind too when we talk about the homework assignments. This theorem 5 on the left-hand side is something that we haven't talked about in class yet, but it explains all of this relation between alpha and the eigenvalues and the runtimes and all of these different things. So I'm going to do a high-level overview of what theorem 5.1 is stating right here, hoping that this provides more explanation, intuition about this alpha value. And I'm going to provide this explanation in context of answering problem 7 over here. So we're really going to be answering problem 7 right here, but I'll do a number of small asides that will help hopefully clarify the issues in those posted onto GitHub. Again, problem 7 on the right-hand side here from notes packet 2, theorem 5.1 on the left-hand side here from the reading. And the text is very small over here. It's hopefully going to be okay. If there's important things, I will rewrite them on the right-hand side over here where we can see them better. Okay, any questions just where we're at mechanically? Okay. So problem 7 here, I'm going to provide an explanation of this intuitively and graphically rather than algebraically, because I think it will give us a better sense of what's going on doing the geometric explanation than the algebraic explanation. If on an exam you were providing one of these explanations, whatever explanation is correct and makes sense to you would be perfectly fine to do. So there is a corresponding algebraic explanation of this, but I'm going to focus on the geometric explanation. And the geometric explanation of a eigenvector is that I will do this in 2 dimensions. In general, we have many larger dimensions. These vectors over here are going to be, again, like something like 10 to the 15th dimensions. But just to visualize things, we'll do it in 2 dimensions here. And let's imagine that our x vector looks something like this. This is our x vector just pointing out in some arbitrary direction. And one of the things that we learned in our linear algebra class is that any vector can be broken up into basis vectors. And I'll happen to have those basis vectors aligned with the axes here. But in general, they don't need to be aligned with the axis. They can be rotated or squished or squashed. But it's easiest to visualize if it's aligned with the axis. And you can always do some sort of transformation to make things aligned with the axis. So that's, yeah, these magenta lines are my basis vectors. X over here is one of these like xk or xk minus 1. we'll start with xk minus 1. Xk minus 1. And recall that in our power iteration, what we're doing is we're saying that x to the k, over here when I have the printed k's, I put them in parentheses to match the notation of the text. When I'm writing it out, I'm going to ignore those parentheses just to keep things less cluttered. But this xk is the same as x parenthesis k, this xk minus 1, same as this x parenthesis k minus 1. And our power iteration says that xk is equal to p bar bar of x, oops, not k, of x to the k minus 1 like this. And it does some substituting in all those definitions for p bar bar to get an equation in terms of p, but this is really like the source of this equation. And let's think about, why does this equation actually work? The reason this equation works is because p bar bar, anytime we have a matrix, we can think about one of these linear transformations as applying to these basis vectors individually rather than to this vector over here. So this can be interpreted, let's keep in red, as p bar bar times the sum over I of some a sub I v sub I, where each of these v's are the eigenvalues, or the eigenvectors, sorry, of this matrix. V sub I is an eigenvector. And each of these a sub i's, it's a little bit hard to exactly interpret what the a sub i's are supposed to be. But the a sub i's are just set so that this whole thing, a sub I, is set so that x to the k minus 1 equals the sum over I, a sub I, v sub I. And it's not obvious that there exist necessarily a sub i's that can do this. That takes some proofs of things, which you probably did and probably forgot from your linear algebra class. But this sort of thing of breaking up a vector into some components, which are eigenvectors of some other matrix, is a thing that can always be done. And in particular, if we have these two vectors right here, this is our, I'll call this one up here, v sub 1 and v sub 2, then the a value, like we're just, in this case, a would be about 1 for each of those two things, because you add those two together and you'll get this, this vector right here. When we do this application of p bar bar, then how does that change our basis vectors? That is equivalent to asking, how does this change our actual matrix or our actual vector? When we say p bar bar applied to v sub I, that's equivalent to asking p bar bar applied to the original vector itself. Well, v sub I, this original v sub I, we know from theorem 5.1 and a lot of other discussion that has happened, is that v sub I, this v right here, this is the top eigenvector. And it has eigenvalue equal to 1. So let's see. I'm going to write it right down here. P bar bar times v sub 1, because the eigenvalue is equal to 1, is just equal to v sub 1 like this. That's the v1 right here having the top eigenvector implies this, that p bar bar times v1 equals v1. But all of the other eigenvalues are going to be less than or equal to alpha. So p bar bar times v sub I, where I is not equal to 1, I is not equal to 1, is going to be somehow less than or equal to alpha times v sub I. It can't say exactly less than or equal to, because these are vectors. It doesn't make sense to say like one vector is less than or equal to another, because it's not a real number. It's a vector. But the way we can get that is with the L2 norm over here. The L2 norm over here. And now this equation holds, and that's roughly what theorem 5.1 is saying, is this thing in orange down here. That when you apply your p bar bar vector to one of these eigenvectors, we're guaranteed to shrink that eigenvector by at least alpha. So over here, when we go from x to the k minus 1 to xk, going orange, the v1 component over here does not shrink at all, but the v2 component over here will shrink a lot. So this is our xk, like this, and it has shrunk by this factor of alpha right here. The xk minus 1 has moved somehow closer to xk, has moved by this alpha factor over to xk, and that's moving us closer to this top eigenvalue, or closer to this top eigenvector. And by repeating this many, many times over and over again, all of these non-top eigenvectors are going to shrink, go down to 0, but this top eigenvector is going to stay the same this entire time. So this alpha value, the reason that it's appearing in our runtimes is because it is the factor by which we're shrinking all of these non-top eigenvectors. It's again, all of these non-top eigenvectors are the vectors that are not the PageRank vector. This v1 over here, that is equal to pi, it is equal to our PageRank vector. And so this alpha factor is the amount, somehow a measure of how much closer we're getting to pi with every iteration. This also explains the almost always true part of this equation right here, because every time we apply this, all of these other components are shrinking. Every component that is not the pi component, that is not the top eigenvector component, is always shrinking. We're always shrinking everything that is not contained in V1, that is not our top eigenvector. So eventually this L2 norm of this vector, sort of like the size of this vector, is going to get smaller and smaller and smaller. There's an implication of that we'll care about here in a second, but before I do that, I've said a lot of things, lots of facts here, easy to be confused about some of them. Are there any questions about what we've talked about so far? Eva.
I understand that the phrase value of the top eigenvector to be uniform.
Yep.
What does that mean, like, in terms of the page rank, like, one?
Yeah, so we don't say that the page rank is 1 because the page rank is the eigenvector itself, so it's an entire vector of things. But the eigenvalue corresponding to that eigenvector is 1, and that's always true for every PageRank problem. The eigenvalue of the PageRank vector is 1. There's a number of reasons why that's true. The simplest one is that every stochastic matrix has a top eigenvalue equal to 1, and the P matrix by construction is stochastic. But there are other equivalent things that have that same implication. I think one of the hardest parts about this part of the class, this very beginning statement or this very beginning paper, is there are so many like equivalent things going on that it's really easy to get tripped up just on like various linear algebra stuff like that. But again, the only way to push through this for everybody, there's nobody who this is like trivial, obvious, easy for. The only way for everybody to push through it is to really try all of these problems, see how much you can do yourself, and push yourself into understanding all the different weird aspects of the reading, asking these great sort of GitHub issues about things. But yeah, Jay first.
This one followed which vector is shrinking by alpha?
So the question is, which vectors are shrinking by this factor of alpha that we're starting at x to the k minus 1 on every iteration, whatever k value is, and we're getting closer to the eigenvalue v1, going from x to the k minus 1 to x to the k by this formula right here, which is the formula 5.1, which is the formula that we're iterating over and over again in our PageRank problem. And so it's every iteration going from one iteration to the next iteration, that vector shrinks by a factor of alpha. Yeah.
Maybe why are we shrinking?
Question is, why are we shrinking to the top eigenvector? So first of all, why is this called the top eigenvector? The answer is because it has the largest eigenvalue. I'm going to zoom in over here on our theorem 5.1 right here. And so each of these, so lambda is a common variable to use for eigenvalues. For p bar, is stochastic. And so the top eigenvalue must be equal to 1. All of these other eigenvalues must be less than, strictly less than or equal to 1. The construction, by the reason we went from p bar to p bar is because of how it changes these eigenvalues over here. and it makes the second eigenvalue be at least alpha smaller than 1. Alpha, by definition, is strictly less than 1. And so something strictly less than 1 times something else less than or equal to 1 gives you something strictly less than alpha right here. And like the proof of that, why is that the case? That's this whole proof thing down here, which you're welcome to read through, but I'm not going to talk about that in class. You're not required to know that. You're required to know like the implications of the statement of theorem 5.1 here, how to understand that. So that's just the literal answer of why this is called the top eigenvector, because it corresponds to the top eigenvalue. The other portion of the question is, why do our vectors, why do our iterations converge to the top eigenvector? And the answer is because of these two equations right down here. That when we apply our p bar bar vector to v1, v1 is the top eigenvector, has the top eigenvalue equal to 1. So p bar bar times v1 is guaranteed to be equal to v1. This here is just the definition of the by definition of the eigenvector. Similarly, this shrinking effect that happens right here is that where every v node is guaranteed to shrink by at least alpha. That's again by the definition of the eigenvector and the fact that the eigenvalue is less than or equal to alpha. So it's an immediate consequence of theorem 5.1 here with the shrinking of these eigenvalues that we're going to be, every time we do this iteration, getting closer and closer to our PageRank v1 vector here, removing these other components from our PageRank calculation. Hopefully that somewhere answered the question in there. Yeah. And again, totally appropriate place to be in for all of this to just like sound like crazy words and not make sense. But the thing that you're responsible for is now that you've seen these crazy words, look at them enough, study them enough over a number of days with appropriate sleep in between those days till they eventually make sense about what they're saying. Very understandable if they don't immediately make sense what they're saying. There are other hands up beforehand. Heather, yes. This part right here? What is what? So the question is, when I went from this line right here to this line right here, what exactly was going on? What is the property of this? Down here in the same orange color, I wrote out that x to the k minus 1 is equal to the sum over I of a sub I b sub I right here. So this here is, when I went from this line up here down to this line right here, it's substituting just this equation right here. And the question is, like, where does this equation come from? Does it have a property at all? And there are, I guess in some sense, it's so fundamental that it doesn't have a name, or at least I can't think of a name about this right off the top of my head. It has a combination of things. Important terms are that the v sub i form a basis of the space. So the basis here is a key word. And all the v sub i's are eigenvectors. V sub i's are eigenvectors. And so the fact that the eigenvectors form a basis is a key thing here. The closest thing to the correct answer to this question about like what is this property called is called the spectral theorem. But if you Google spectral theorem, you'll find something very scary that you don't need to look at. So this is a consequence of something called the spectral theorem. But that is a very scary thing to Google. Those are the other keywords. The fact that the eigenvectors form a basis is the key thing there. And this fact is also explained in the reading up through these relevant sections right around theorem 5.1. That's a good question. Yes, question?
I wanted to ask how this relates to definition of know that UMR is greater than one.
Yes, I'm going to stop you. So the question here is, how does this relate to the definition of primitivity? And this is also specifically one of the things that was asked in those issues. The answer is that, so primitivity has one top eigenvalue on the spectral circle. There's a many of equivalent ways of saying that. One equivalent way of saying that is that the top eigenvalue is unique. Here, this theorem 5-point run right now is telling us all of the eigenvalues. We have these specific eigenvalues right here. And by stochasticity, so P bar being stochastic, P bar stochastic implies that all of the eigenvalues are less than or equal to 1. So I wrote out all eigenvalues here, but that's equivalent to all the lambdas of I less than or equal to 1. And that combined with the fact that alpha is strictly less than 1, alpha is strictly less than 1, this implies that alpha times lambda 1 strictly less than or equal to 1. Alpha times, I guess they use L2 right here, so I'll change that. Alpha times L2 strictly less than 1. So this thing right here, strictly less than or equal to 1. So the top eigenvalue right here is 1. The second top eigenvalue is strictly less than or equal to strictly less than 1. In fact, strictly less than alpha. And so this theorem 5.1, this is where we get that primitivity from. So one way of thinking about the alpha hyperparameter, the alpha value, is that it's a measure of how primitive we are. That the smaller alpha is, the more primitive we are, because the farther away we are from having two eigenvalues that are the same. And the larger alpha is, the closer alpha is to 1, the closer these two top eigenvalues are going to be to each other. And so the less primitive we are. Primitivity itself is a strictly binary relation. You either are primitive or not primitive, but a lot of these binary relations have some sort of way of measuring how much you are of that. And so alpha, you can think of it as how primitive you are. Good questions. Did that answer your question? Go ahead. Yeah, alpha is strictly less than 1. That's just by the definitions. And so that implies that alpha, so something less than 1 times something less than or equal to 1 must also be less than 1. All fantastic questions. Probably a lot of you still have questions about what's going on, and they're just like so vague they don't even know how to ask them. Probably some of you feel like you might know what's going on, but tomorrow you'll look at your notes again and once again have no idea what's going on. Again, appropriate way to place to be at. That happens a lot in this sort of thing. So as you're working through these issues, working through these problems, if any more questions come up about this, feel free to come to office hours or ask me after class today or other times, and we'll work through those together. But this is a good stopping point for us for today on this topic. The other two things that we're going to do today, at least two things that we want to do today, is going over this update for today notes right here. Right now I'm in the topic 1 folder on the computation PageRank in class, and so I have a handful of notes for us that we will be going over today. Two important administrative-ish things. Our first is the project has been posted, and then we'll talk about the midterm exam after we talk about the project. So for the project, there is again a project folder in this repo you can click on, and it will take you to this description of what to do down here. At a high level, I have scraped all of the web pages, all of the posts, all of the news articles from this URL right here, lawfareblog.com. This is a website that provides legal analysis on different US national security issues. And you are going to use PageRank to write a search engine for this website. And your search engine will return only the most important results from this website based on whatever your search term is. And so I have some various examples below related to things like coronavirus or President Trump or different issues related to the law and national security issues. And you will have to find the most important web pages in this domain right here. Your due date for this is this coming Sunday. And the late policy for this assignment is that you will lose 2 to the -1 points, where I is the number of days late. So if you submit on Monday, that'll be 1 day late, -1 point. Tuesday, 2 days late, -2 points. Wednesday, -4 points. And Thursday, -8 points, 0 credits. Your collaboration policy for this assignment is you can do whatever you want that will help you learn, but be an adult about it. You may talk to other students. You may use Google ChatGPT. But again, the real point of this assignment is that you are going to have an in-person oral exam with me, and you'll have to be able to explain all of these concepts to me. And so the purpose of this assignment is to help you understand that. As an example, one of the tasks that you're going to be doing in this assignment is selecting different values of alpha and seeing how that affects the runtime versus the quality trade-offs of your project here. And so working on that will hopefully help make some of the discussions of things that we did today more clear. Any questions on just administrative things about the project? Okay. I will highlight again that I have the office hours on Friday morning, so I definitely recommend starting this before Friday so that if you do have questions about things, you'll have at least that office hours period to get those answered. My solution here to this project is about 10 lines of code that you have to write. So it's not a lot of stuff that you have to do, but it will take, I don't know, some time working through details and debugging things to get those 10 lines of code correct. Okay, I'm gonna do a quick background here. I'm not gonna go through the entirety of this assignment. There's a lot of stuff in this README here, but just some quick background notes. The first is there's 2 data sets that you'll be working with. They're both contained in this data folder, and they're both what are called CSV files that have been gzipped in this .csv, .gzip format. I have a number of examples here of how to use these files. So here, this program called zcat is one that is available on all Linux machines. On Macs, it is something that you can install with Homebrew pretty easily, but I don't believe it's installed by default. On Windows machines, if you have the various Linux sub-packages installed, it's available by default. But if you don't have those installed, it won't work at all. That said, you don't have to run any of these commands right here. The purpose of these commands, all the different terminal commands that I have, is just so that you can see the output of some sort of explanation that I have up above. So here, this is the purpose of this command right here is just to show you what the format of this file looks like. And it's you don't actually have to run this command yourself. You're welcome to, but you don't have to. This small.csv.gz is the same graph that is contained in the PageRank paper. So you'll be able to implement things, get it working on this very small graph, get very fast turnaround time on your debugging. And then once you get things working on this small file, there's another file that contains the actual data set for this blog post that you'll work on. Let's see, coming down here, this tells us how many different links are in our graph on this blog post file. And there are 1.6 million links. So this is enough where you can still run this algorithm entirely fine on your laptop. It only takes like, I don't know, less than a minute to complete. But you'll have to actually do things correctly with your sparse versus non-sparse matrices. That if you use the dense matrix, you'll get a much worse runtime. This quadratic is very slow, whereas this linear is very fast. There's a lot of different background things here. There's only 2 coding things that you'll have to implement. They're both annotated by fix-me annotations in the corresponding files. If you click this link right here, then it'll take you to the actual implementation, or the note there of what you have to implement. And there's a hint that gives you the specific functions that you should look up in the Torch library, whatever you need to do. So this should be mostly self-explanatory. I'm not going to go through code-wise how to use things like PyTorch to do this. I'm going to expect that you all can figure that out on your own. The hard part about this assignment really is not the coding so much as understanding just what those math equations are supposed to do and get them implemented. Jumping all the way down here now to the submission section. To submit this assignment, you'll be creating a new repo on GitHub, not forking this repository. Then there's a handful of commands down here that I want you to actually run, and you'll just paste the output of your command in this code block down here so I can see what the output is. And I will grade these assignments by looking at your README file, looking at all these commands, and checking to make sure that the output for these is what it should be. After you do all that, you'll put all your stuff on GitHub and submit the link to Sakai. One last thing that you'll have to do is make sure you get 5 different stars from your repository that they can be other people in this class. But this big long note here explains why we're doing that. And it's basically to hack the pagerank algorithm that recruiters will be applying to your GitHub profiles when they try to recruit you. If you do a search on GitHub, you'll see that, so this link right here takes you a search to all the repositories labeled data mining. And you can see that they're not like ranked directly by things like the most number of stars, because here we have a 1.7 thousand stars ranked below 1.6 thousand stars. And so the way that basically every search algorithm everywhere on every website that you interact with, the way that it decides what things are more popular are somehow using PageRank to rate all of these repositories. So you're welcome to read through that, all these links if you'd like. But the important thing here, yeah, submit your repository to Sakai. Any questions about administrative things with this assignment? Okay. Coming back to our notes for the week here, under topic 1 then, is about the midterm exam. So your project is worth 8 points. You have 8 points that you've already done in class between the 2 quizzes. Your midterm exam, though, will be worth 32 points. Your next midterm exam, 64 points. And your final exam, 128 points. So your exams really form the bulk of your weight in this class. And again, they will all be in person in my office. In order to sign up for an exam, click this link right here, and it'll take you to a Google spreadsheet where you can sign up for different exam slots at different times. And if any of those, if those available times don't work for you for whatever reason, let me know and I'll open up some more time slots that work for you. But these are all various times starting this coming Friday if anybody wants to take it earlier, but various times that I'm available next week to take the exams. The format of the exam, the time slots are for 30 minutes. I expect that on average, the exam will take 20 minutes. And the first thing that will happen is I will start by asking you to explain either the power method or the exponentially accelerated power method. I'll just basically roll a dice, and that'll determine which one of these 2 things you will be telling me about. So you should prepare in advance a 2 to 5 minute explanation of each of these methods so that whichever one comes up for you, you are able to immediately tell me about. And your explanation should cover all the important formulas for the method and how to get the runtime of that method and why that runtime is important, whether it is good for the web or not good for the web. Based on exactly what you say to me during that 2 to 5 minute presentation, I will ask you a series of follow-up questions. Some of those follow-ups will be directly from the notes packet. I will just open the notes packet and point to a particular question, and you will read it and explain to me the answer on the board. So the best way to study for this portion of the exam is to actually complete all those note packets, make sure that you understand how to complete all those problems, because any one of those problems is fair game for the midterm exam. There will probably be 1 to 3 questions of this type, depending on exactly how the conversation is going. There will also be a number of possibly smaller questions that will I'll ask as you're saying something, and I might just interrupt you for a second and ask you to clarify something for me. But the two things that you definitely want to do to prepare are this 2 to 5 minute explanation of both the power method and the exponentially accelerated power method, and knowing how to do all of the questions on all the notes packets. If you can do that, then you'll probably get an A. In terms of the actual grading, I do have a syllabus that I'll be using to grade everybody. I'm not going to tell you all what it is, though, in advance, because it's not useful for you. You should just be thinking of this as one of my previous students who did this described it, a vibes check of your understanding of things, and you want to pass that vibes check. I will be grading you primarily on the correctness of all of your answers. If you do say something wrong, though, that's not the end of the world. It's I will try to find ways to help you figure out that you said something wrong and correct yourself. So as an example, last time in class, I said something wrong about the runtime of the pagerank method, giving us a quadratic runtime. If you were to write something like that on the board, I would ask you why a quadratic runtime is good or not good for the pagerank method. And hopefully that would click in your brain that, oh, this is n is too big for quadratic, and so we can't do that. And that would let you fix your answer. And if you are able to, if you see a mistake that you've done and you fix it, then you definitely do not lose any points for that. That's only a good thing to find a mistake and fix it. But if you do say something wrong confidently, that's worse than saying you don't know. So make sure not to say things wrong confidently. If you do say something wrong, but you're explicitly telling me that you're guessing, that's a good thing, as long as you make it clear that you're guessing and explain why you think the justification is the way it is. And it's possible to get full credit on answers with a response that you're not 100% sure about, that you acknowledge as a guess, as long as you are providing good justifications for why that guess is the way it is. Again, one of the purposes of having the in-person oral exam is to prepare you for like technical interviews or other situations where you have to describe technical concepts to other people. And these are the sort of things that technical interviewers want to see from you. They want to have people who, when they make mistakes, admit to them and say how to fix them. Or when they don't know what the answer is, they want to see people clearly state that they don't know what the answer is, but figure out some ways to make some educated guess about what the answer might be. So the grading will reflect that. You'll sort of be indirectly graded on your presentation, not directly graded on your presentation, but the only thing you're directly graded on is the correctness of your answers. The way that you're indirectly graded on your presentation is if there are presentation things that make it hard for me to understand what you said. That makes me not able to give you credit for the correct things that you say. Common mistakes that students make is that you try to understand all the material, but you don't ever actually practice writing it on the whiteboard. We'll be in my office. You'll have a whiteboard available to you, and you should be explaining everything using the whiteboard and verbally. So practice actually using the whiteboard, writing on it in front of other people as you explain your answers. Also, do not mumble. It makes it a lot harder for me to give you credit for things if I can't hear what you're saying. Also, don't waste time talking about trivial things. One of the strategies that some students try to do, often out of nervousness, is just like talk about their weekend or other things like that on the exam. You want to get right into just telling me all of the things that you know and get points for those things. We'll just get straight into doing the exam stuff. You want to spend as much time as you can demonstrating your knowledge about different things, and short, succinct answers, much better than longer, rambling answers, because if you say something incorrect in a rambling answer, which you're likely to do, you will lose points for that. So practice being as short and succinct as you can. If I have follow-up questions, I will ask them, and you will not get docked points for the fact that I am asking follow-up questions. Few last things here. You may not use any references or computers. So again, mimicking the environment of a technical interview, just like the knowledge that you have in your head is what you're allowed to bring in with you. There's not going to be any situation where you have to do like a crazy calculation. If you think you have to do a limit or something to calculate big O notation, you can just tell me what is the limit that you wish you knew the answer to, and I will tell you the answer to it. That's the sort of thing, again, on a technical interview that's very appropriate to ask the interviewer or state, like, I don't know exactly what this thing should evaluate to, but based on whatever it evaluates to, I would judge the answer to be this way. And then last thing, I will give you your grade immediately following the exam, so you'll know exactly how you did and maybe what you need to improve or continue doing for subsequent exams. This exam is, again, 32 points, so it's the biggest part of your grade at this point, but the subsequent exams will be much larger parts of your grade. So if for whatever reason your grade is not what you hope it is after this first exam, you'll have lots of other opportunities to improve your grade in the future. Okay, I said a lot of things. Any questions about any of the format administrative stuff of the exam? Yeah.
Did you test us on the computational linear algebra?
Question is, would I test you on the computational linear algebra notes? And the answer is that if I think you are weak on that, I might. But the focus is really the pagerank stuff. So you should understand the linear algebra, the computational linear algebra stuff to the extent that it's needed for the pagerank, which is basically understanding everything in the linear algebra notes. If I see that you're struggling on the pagerank stuff because of the computational linear algebra stuff, I might ask you the computational linear algebra stuff to try to help you get some points from that. Yeah, good question. Any other questions about anything related to the exam?
Wait, did you say that, like, asking follow-up questions means losing points?
No, asking follow-up questions does not mean losing points. Whether you are asking me follow-up questions, clarifying something, or whether I am asking you to clarify something does not mean points taken off. It probably actually means that things are going well. Yeah, it can be like intimidating if I'm interrupting you to clarify something, or it can be nerve-wracking if you didn't understand what I said and you want to ask me something to clarify that. But both of those things are actually signs that things are going well. Any other questions? Okay. Wednesday in class, we will start new material. But today we'll do some more review for another 20 minutes about the PageRank stuff, helping you prepare for this exam. I want to go to the notes 3, and we'll talk about the notes 3 starting from the top. So far, this notes 3 packet, again, the only thing that I've done is said that you'll need to know that exponentially accelerated power method. I haven't even talked about what it is. You'll have to review the notes on your own, make sure you understand what that is. If you don't understand what that is, which is, again, totally okay, then you'll have to come to office hours to get that clarified, or figure it out with other students. But part of the, I guess, bigger picture meta things that you're supposed to learn from this is understanding working with algorithms that haven't been explicitly taught to you, but just from reading the descriptions of those algorithms. So that's the only thing that we've talked about on notes PageRank 3 right here. We're going to start today, or finish today, talking about some extra motivations for PageRank and why you might want to use them in different situations. I think this can help give you some clarity about some of the purposes of why things are the way they are. And again, I don't know, this comic up here, the right way to prepare for this test is you can't just like sit down and read things. You can't just sit down and memorize things. You're going to have to work through these problems. And these problems are all difficult enough, even the trivial problems, that you, no matter how much time you have in one sitting, you can't do them all in one sitting. You have to actually like do a little bit at a time, different days, actually fight with it, not just sit down and think it'll come to you easily. But problem 1 here. So describe how PageRank can be used for the following tasks. I have 2 different tasks here that you'll have to talk about how PageRank could be used for this. So you are in charge of advertising the new Apple iGadget, and you want to deliver free samples to Twitter influencers with the hope that they will write good reviews that cause many people to purchase the iGadget, whatever it is. How do you select which people to give these free samples to? Lots of different ways that you could do this, but your graph, maybe, will be the different, maybe the graph nodes could be all of the different iPhones that are in existence. Every iPhone is a node. And the edges are if two phones have called each other. So this is different than the web example in the paper, but this is a graph, has nodes and edges, so we can run pagerank on it, and the pagerank vector, now pi, will give us somehow the most influential iPhone users. Because somehow they have been, they're most likely to talk to other people. That if you give the new iPhones to these top people, their influence will spread to the largest quantity of people throughout the graph. There's lots of different ways that you could do something like this, but this is an example of one of them. Are there any questions about this? Okay. It's a relatively less technical problem, so hopefully something like this, questions like this make sense, relatively easier to answer. Problem 2, this is going to I'll do a little bit more complicated example here using the personalization vector, something that we haven't talked about explicitly. But in problem 2 here, it says you are the director of the CIA, and you want to kill terrorists, like the CIA does. How do you identify likely terrorists? Well, we can use the same sort of graph that we had before, where the nodes are phones. And the edges are calls between phones. But at this point, we haven't actually included any information about like terrorists here. That comes in our personalization vector V. The personalization vector can be 1 for all known terrorists, 1 for all known terrorists, and 0 otherwise. We'll draw a graph about next to help illustrate exactly what's going on here. So if we have, say, like 1, 2, 3, a little bit more complicated graph than we've had in the past about things. And maybe here in this graph, the top page rank with a standard personalization vector would be 1 over here. This will be the top page rank with the standard personalization vector V equals to the E over N, the E being all ones. And I think we've sort of talked through that a little bit before. But if we have now that 5 here is the known terrorist, then when we do our sort of random surfer model, the PageRank vector here, I'll draw in magenta. This is the personalization vector. So these values all have 0 over here, a 0 and a 1. 0.5 over here is a known terrorist. The personalization vector, again, comes into play when we have a plus EV transpose over N, adding that P bar bar equals a bunch of stuff plus this. This EV transpose is like where when we enter our graph to do our random walk, where we start from. And now we'll only start at 0.5 over here, never start at any of these nodes. And 5 links to 4 up here. So 4 will be the top page rank. With the new personalization vector, with new personalization vector. This idea of like coming up with clever personalization vectors in order to make your PageRank shape it in a certain way that is useful to you is something that you will explore in some of the tasks on the project. This is just one example here where how the CIA might use this. I will pause for questions in a bit, but down here there's a link to the director of the CIA, Michael Hayden, General Michael Hayden, talking specifically about this. And so I want us to watch that clip here in class for a second. It's less than a minute long, but he will tell us how they use that.
General Hayden, you can find out all these things David just said about me, about David, about anyone in this audience.
Oh man.
That is a function of.
Well, the audio is not going through to the speakers out here for some reason, and my audio is not going to go up.
Operational
Maybe I'll try it.
I'd like you to talk about whether you're comfortable with that operational capability. If so, why, and how often is it used in the ways that David described?
Yeah, first of all, David's description of what you can do with metadata, mutual friends do it, absolutely. We kill people based on metadata.
Yeah, it's probably hard to hear. He just said we kill people based on metadata. The specific thing that he's talking about is exactly doing this with PageRank and exactly doing this with people's cell phones and assigning their personalization vectors in the right way. So it's worth. Yeah, I apologize the audio didn't come through here, but it is worth just watching that 1 minute clip on your own. Any questions about the, I don't know, technical aspects or non-technical aspects of the PageRank personalization vector example here? Okay. Okay, maybe I will give some highlights here about the intuition behind this exponentially accelerated PageRank method then in our last 10 minutes of class here. In order to do this, I'll use the blank page right above it. The idea of this EAPM algorithm is, so we talked about a lot in the first set of notes about how reparenthesizing things can make our runtimes very different. And the idea of this EAPM is to reparenthesize the power method for faster runtimes. And our computation, again, looks something like k, or x rather, x to the k equals p bar bar x to the k minus 1. And if you unravel that, so this is a recursive definition where x has some initial value. And if you unravel this recursion, you can say that this is equal to say, p bar bar, lots of these p bar bars, k times our x, whatever our initial x value is like this. Or to be a little bit more succinct, something like p bar bar to the k times some x naught, where this is a matrix exponential right here. Exponential, which means just the same exact thing as the regular exponential of multiplying things a bunch of times together. And by re-parenthesizing this carefully, we can greatly reduce the total number of matrix multiplications that we have to do. So if we have k equals 8, in the example of k equals 8, we have, say, I'll actually draw out 8 of these p bar bars. 1, 2, 3, 4, 5, 6, 7, 8. Instead of doing 8 of these multiplications together, I can observe that one of these p bar bar times p bar bar, call that a. I only have to compute a once, and that gives me all of these things right here. So compute a only once. And then b, if we call that a times a. So over here, a equals p bar, b equals a times a. We've only computed a once, and now we've computed, now we can do b times b. And then one last thing of c equals b times b. Now with only three matrix multiplications, this is only 3 matrix products, 3 matrix products. I'm able to do the computation of these 8 matrix products altogether. So instead of having 8 matrix multiplications, reduce it down to 3. If we go up one more level, instead of doing 16 matrix multiplications, we go down to 4. So it's called exponentially accelerated. We get that extra log term in our runtime because of this parenthesization right here. The notes down below, the notes down here, they give you a little bit of a formal definition. These notes give you a formal definition of all that. This KQ, or yeah, QK right here, are these A, B, and C values. So this right here, A would be Q1, B would be Q2, and C would be Q3 in the notation down below. But the intuition here is we're just adding a bunch of parentheses around these different matrix products, and that's what's making our system potentially faster. The downside here is that, as you will see, you have to do dense times dense products, and so that's where the n cubed from the runtime is going to come from. This is an example of what's called a divide and conquer algorithm, because we are dividing up the problem into many small different steps and solving those problems individually and having a clever way of combining those problems back together. So this is an example of a divide and conquer algorithm, a very common strategy for getting faster algorithms. Any questions about the intuition on this problem right here?
Can you explain the matrix products again?
Explain the 3 matrix products. Yes, so originally I had in my example right here of we have k equal to 8. So there are 8 p's being multiplied together right here. And the naive way of doing this, the way that we were doing it in the original power method, is doing one by the other, going from left to right. And so there are 8 things that need to be multiplied together that way. The new way of doing this is to add parentheses that would look something like this around all these. So the square brackets up above indicate parentheses. And then observing, if I do this p bar bar times this p bar, I don't need to repeat that same computation, because that's, we can just store that in a variable, call it a, and now we have a for us already, so we don't have to redo those computations. Similarly for b, b would be a times a. We don't have to do that twice. We can just do it once and not do the other computation explicitly, just reuse that variable. So we have 1 matrix multiplication on A, 1 on B, 1 on C, 3 levels of multiplications that we're doing. So there's only 3 matrix products that are happening instead of the 8 from the original. So that's the intuition behind why this is potentially faster, because it results in fewer matrix multiplications. Any other questions about anything? Okay, then yeah, we're a little bit early. We'll just end early today. If you do have questions about things, happy to stick around after class and get those answered. Also, office hours Tuesdays and Fridays now. And strongly recommend starting today preparing for the midterm exam next week.